I'm Praveen. I'm an engineering manager at Crowdstrike, Australia, and today I'm here to talk about real-time adaptive controls. This is what I'm going to cover in my talk today. I'll start discussing the need for real-time adaptive controls. I'll introduce a reference architecture using which I drive the rest of the talk. I'll briefly discuss the adaptive controls and summarize it all in the end. There is a lot to cover here, so let's get going. As microservices gain more and more popularity, building for and deploying on distributed architectures is becoming the de facto standard for these container workloads. A direct consequence of this is the explosion of configuration surface for these container workloads. Much of this configuration include tunables such as worker pool sizes, auto-scaling policies, throttlers, circuit breakers, etc. And these directly affect the service resiliency and are often critical in nature. While these techniques provide an accurate value at that moment in time, the measured ideal value for tunable would quickly become stale as systems topology change due to partial outages, auto-scaling, or from code pushes that impact system characteristics. We wanted to do better than static configurations. So we sought to automatically identify a system's inherent ideal configuration in a way that would require no manual work, require no centralized coordination, infer the limit without any knowledge of the hardware or software topology, adapt to changes in system topology, easy to compute and enforce. To make the discussion in this talk more concrete, let me introduce a reference architecture and drive the rest of the talk using the workloads from that architecture. There are two services in our reference architecture. A writer service that reads from a message bus, say Kafka, transforms the data and writes to a persistent store, say Cassandra. The actual technologies are not really relevant here. A reader service that exposes an API interface using which the clients can make queries and read data from persistent store. Now let's talk about various controls that are in place to make these services more resilient. We will discuss the challenges with the traditional static controls by going through example scenarios and conclude by introducing the adaptive variant of each control or pattern. First up is concurrency. Let's zoom into the writer service from the reference architecture. Each writer in this architecture is a Kafka consumer, and it has multiple workers in it. This worker count is configurable as well. We configure this to a predetermined number when we deploy a new service and also update this from time to time as per need. Now let's go through some scenarios to understand the challenges with having a predetermined fixed number of workers. In this scenario, the Kafka topic is empty and the workers are not doing any work other than just polling Kafka for new messages and are potentially wasting CPU cycles. Now say we have some traffic and Cassandra is in good shape and the consumer is performing quite well. But since we are running same number of workers as we are when we were empty, maybe we are potentially not utilizing all the processing capacity that a pod is capable of here. Maybe we can run more number of workers without overloading the system. Now, let's say that Cassandra is exhibiting downgraded performance. But given that the worker pool size remains static, regardless of the feedback from Cassandra, we would eventually overload Cassandra, which might lead to cascading failures. Surely, backoff strategies would help here, but is backoff alone sufficient? And how is it related to concurrency of our writer service? Before we answer that, let's take a detour and explore queuing theory. And let's explore Little's law in particular. Little's law is a theorem that determines the average number of items in a queuing system based on the average waiting time of an item in that system and the average number of items arriving at the system per unit of time. Now let's see if we can apply the principles from Little's law to model the processing capacity of the writer service. Now we can clearly see that the number of workers is synonymous to the arrival rate from Little's law, as the number of workers influence the arrival rate of messages into the system. I mentioned a couple of slides ago that backing off can help in the case of an overloaded system. But now, thanks to Little's law, we are able to see how this is related to the concurrency of our system. This illustration helps us come up with a mental model to understand the interplay between backoff and concurrency strategies and how both together can influence the total capacity. Backing off can increase the average processing time for a particular message, and the concurrency of the system, number of workers in our example, can influence the average rate of arrival rate of messages. If you're following closely, you will identify the underlying theme that we're trying to capture here is that capacity is not constant. The capacity of your service's downstream systems might change over time, and hence there is a need to change the processing capacity of your service. Concurrency combined with appropriate backup strategies is a great way to do that. So, if the capacity does not remain constant, how do we estimate the right number of workers? Not only is that it is hard to estimate, but also would be an operational nightmare if we were to keep estimating this and update configuration periodically. Instead, we can infer that based on the feedback from downstream system and change this dynamically in real time within permissible bounds. The beauty of this is that the ideal capacity does not need to remain constant. As the ideal capacity changes, the feedback from the downstream system changes, and we adapt accordingly and eventually converge with the ideal capacity. There are many strategies using which we can adaptively change the concurrency of our services. Majority of this adaptive capacity management theory took its shape through TCP congestion control. We wanted to start with the simplest of all, so we picked AIMD. AIMD algorithm is a feedback control algorithm best known for its use in TCP congestion control as I just mentioned. AIMD combines the linear growth of the congestion window when there is no congestion with an exponential reduction when congestion is detected. In our scenario, we can model congestion using the right timeouts to Cassandra data store. Now let's see this in action. Here we can see as the Kafka topic is receiving more traffic, we can see the adaptive concurrency increase the number of workers in our writer service to match this demand. And once the lag was consumed, the worker count was reduced to near minimum levels automatically to save CPU cycles. This is another example from our production systems where adaptive concurrency is really a game changer. As opposed to the previous example, the number of workers have not increased initially here, even though there is significant spike in traffic. This is because the adaptive worker pool noticed the elevated latency from Cassandra downstream and avoided overloading the system. When the latency was down to normal ranges, it automatically increased the number of workers to bring the processing pipeline up to date. Now let's take a look at rate limiting. We will use the reader surveys from this reference architecture that we've seen before to help put things into perspective. Traditionally, rate limiting is done through central coordination using a fast in-memory store like Redis to host the rate limiting configuration. Clients make requests to readers, and readers, upon receiving these requests, will check the central store to either allow or reject requests. Also, it is not uncommon to use a local in-memory store in the reader containers itself that periodically update the configuration from the central store. Both these designs require centralized coordination and have single point of failures, especially when the central store is down for an extended period of time. Even if we ignore the coordination problem, there are still some shortcomings with traditional rate limiting. Let's go through a few scenarios and see if we can surface them. The first scenario is as follows. Say we have 3 clients A, B, and C for the reader API, and the request rate allocation is 10 requests per second to A, 25 to B, and 5 requests per second to C. Let's say if one reader container can serve 100 requests per second at a given point in time, with this allocation strategy, we are only utilizing 40 even with the peak usage from the clients. We are unnecessarily rate limiting clients when we can process more of their requests, so we are essentially wasting capacity. Now let's look at a scenario where we have reader API container scheduled on, say, a busy node and is getting quite heavily CPU throttled. The total capacity won't be 100 requests per second as we have seen before, but it will be degraded. Say now the capacity is just 20 requests per second, as the container is basically struggling to get CPU time on this node. But with a static configuration for clients, we still allow 40 requests per second to land on the system. This will lead to resource exhaustion and eventually might lead to latency spikes or memory leaks if not handled properly. Finally, in this scenario, we challenge the fundamental assumption that we can guarantee to process 10 requests per second for A and 25 for B and 5 requests per C at any single time. For example, when Cassandra is exhibiting downgraded performance, we won't be able to serve that number of requests. But the clients A, B, and C will keep making requests, and these requests won't get rejected because they are within limits, and it gets really bad from there. Without load shedding, we will eventually end up with cascading failures. So how can we improve upon this? Following the theme of this talk, we respect that the capacity of the system doesn't remain constant, and we adapt to its changes. Let's see how we can do that with respect to rate limiting. The idea here, instead of allocating A with 10 requests per second, what if we allocate A with 25% of the total capacity? And we do similar allocations for B and C as well. The problem is, what about T, the total capacity of this reader container? How do we estimate that? It is simple. We don't estimate that. We infer that from the system. This is the same approach that we used for determining the number of workers for the writer service. We start with a seed, max and min bounds, and we let the algorithm converge around the ideal value for T by adapting to the feedback from the downstream. This adaptive rate limiting system requires no manual work, and it requires no centralized coordination. It is super easy to compute and will not steal resources from the service. We can infer capacity limits without hardware or topology awareness, and we will be able to adapt to changes in downstream or processing capacity. Next up is autoscaling. Traditionally, autoscaling for containers is based upon resource utilization metrics like CPU or memory, or external metrics like incoming requests onto the container or the consumer group lag on a particular Kafka topic. This usually works great for stateless services or services without any downstream dependencies. But the issue with that autoscaling system is that it is an open system. It only takes load that is coming into the account and doesn't respect the feedback from the downstream, leading to potentially overloading of downstream systems and causing cascading failures, which we all want to avoid. So how can we improve upon this? Following the theme of this talk, we respect that the capacity of the system doesn't remain constant and adapt to its changes. Let's see how we can do that with respect to autoscaling. So let's say we are using adaptive concurrency with the following configuration. We have 5 as max number of workers and 2 as minimum number of workers, say in a writer pod. And now we have an autoscaling strategy which says when the utilization of this capacity is greater than 70% for say 10 minutes, we scale up, and we scale down when the utilization is less than 50%, say for 10 minutes. Let's explore a few scenarios that will help us understand how using adaptive concurrency, we can build an adaptive autoscaling strategy. Imagine a scenario where we have 2 pods with 3 workers in it. Now, the average capacity in this scenario is 60%. But if we have no lag in the system and there is no work for the adaptive concurrency system to work through, it will reduce the worker pool size, as we have seen before, to minimum size and to try and save resources. In this scenario, the average capacity utilization is 40%, resulting in a scale down. When we have lag growing, there is a lot of work coming into the system, so the adaptive concurrency increases the worker pool size if the downstream allows it to say 4. So now the capacity utilization is 80%, and this should result in a scale up based on our autoscaling strategy. Now that we understand the math behind this, let's go through an adaptive concurrency system and look how we can use worker pool capacity utilization to drive an autoscaling strategy. At the top of the screen, we have 1 pod with 4 workers in it. The utilization in that case is 80%, which is greater than 70%, and our autoscaler will notice this and adds 2 more pods. So now we have 3 pods with 4 workers each. And let's say that is too many workers and we are overloading Cassandra at this point. Cassandra's performance will be downgraded and we start receiving errors. Adaptive controller will adapt to this and reduce the number of workers in each pod to 2, which is the minimum. But when we run with 2 workers for some time, our capacity utilization will be less than 50%, so the autoscaler will scale down the deployment by 1 pod. So now we have 2 pods with 2 workers each. Since this is too low, the success rate is pretty high, and the adaptive controller sees this opportunity and increase the worker pool size to 3. In this hypothetical scenario, if 2 pods with 3 workers is the ideal size, the adaptive controller converges here and the worker pool size is stabilized. This autoscaling system is a closed loop system. It respects the feedback from the downstream indirectly using the concurrency pool utilization metrics and adapts accordingly. Also, similar to traditional autoscaling systems, it can autoscale whenever there is a need to based on the incoming traffic, and hence closing the loop. However, there is one last challenge. At the heart of this autoscaling strategy is the max number of workers. How do we estimate that? We went back to academic research on system scaling to understand the best way to empirically estimate the maximum number of workers. The idea here is to establish the relationship between the number of workers and your throughput through experimentation under ideal conditions, and that gives us the visibility to estimate the theoretical max at which we get the best throughput. Once we have this theoretical estimate, we can probably pick a threshold, say 80% of theoretical maximum as our practical maximum. To summarize what we have discussed today, we have seen how we adapt to feedback from downstream and change the concurrency of a system dynamically. We have seen how we can utilize relative capacity thresholds instead of static rate limits. Also, we have seen how we can make closed-loop autoscaling decisions based on the adaptive concurrency metrics. Combined, these strategies help increase the resiliency of the system. If you want to work on awesome distributed computing challenges like these, check out our careers page. We have a lot of open roles across various teams and all over the globe. I am hiring engineers in Australia, so please reach out to me if you're interested. Thanks so much for the opportunity.